Good morning, ladies and gentlemen. I'm Nerissa Chu. I'm on the Board of Governors for Consumer Electronics Society. It is my honor and my pleasure to introduce two outstanding entrepreneurs on the stage, Ariel Garten and Dr. Tim Mullen. They have already spent the Saturday evening with the young professionals where their bios were pretty much read by me with a few mistakes. But all that information is on the web. So I'm not going to take any more time now to leave the time for them to share with you the technology and the products they have come up with, which really blends computational science, cognitive neuroscience, and arts in a rather unique way. But I do want to mention two things, though. One is Ariel Garten's company's product, Muse. She's the CEO of InteraXon that is based in Toronto. And Muse was noted as the most important wearable product in 2014. And Tim Mullen is the CEO of Syntro, which is also known as CUSP, and their NeuroScale is the world's first biggest API service for neuro-related data, including EEG. And he also brought in the EEG lab to open source and for the consideration of standards. So there were at least 4 standards that were provided for the industry to take advantage of. So without further ado, I'd like to introduce our first speaker, Ariel Garten. Please join me with a round of applause for her speech.
Good morning, everybody. How are you? Great. I'm here to talk about brain-computer interface, past, present, and future. So as we know, the idea of connecting directly from your brain to a machine, from your brain to a computational device, has been capturing our imagination for decades. Well, this technology has now moved out of the laboratories, out of our imaginations, and into reality, actually onto consumer electronics shell. Now, we all know to make something that is a consumer electronic and to make it successful, it has to be incredibly simple, really easy to use, so easy your grandmother can use it, and so robust your 3-year-old can bang on it. I'm going to take you through the rich history and the technical background of brain-computer interface and how we get from this rich history to a very simple consumer device that we can use today. And then Tim Mullen is going to take you through the signal processing, the background, and how we take this technology into the future. So brain-computer interface is actually quite old. It started in the 1970s. The term was coined by Jacques Vidal. And then even in the 70s, you start to see interactions where people are creating simple technologies where you can modulate sound with your brain. This is David Rosenboom and his early 1970s experiments. From this early beginning, you end up with things like games of Pong that 2 people in an MRI machine can play against one another. You end up with the technology that came out of BrainGate and Donaghy's lab, where an individual who's with an implanted BCI can control a robotic arm very slowly, after much training, but actually take a robotic arm and sip a cup of coffee. You end up with complex interactions where you can have real-time signal processing and real-time neuroimaging with high-density EEG, the kind of imaging that you'd only be able to see with MRI in the past, that you can now do in a wearable form factor. And then you even end up with toys on the shelf where a kid can be a Jedi and actually control a little ball in a tube with the Force using his brain. There are lots of ways to implement a brain-computer interface, some more practical than others. This is one of the less practical ones, using an MRI to track the hemodynamic response. More practical is using functional near-infrared spectroscopy, FNIRS, which also tracks the hemodynamic response, but can do it in this very small form factor. This is limited in what it can do because the time course is very slow. It takes about 5 seconds for your hemodynamic response to change, for us to know that something's happened in that area of the brain. But combining these kinds of technologies with others, you end up with rich dynamical interactions. Another way to do brain-computer interface is to write to the brain. And we're actually starting to see a new generation of technologies come up that actually let you electrically stimulate the brain, transcranial direct current stimulation. You're even finding some of these on consumer shelves, products like the Think or the Focus. TMS, transcranial magnetic stimulation, is available only in clinical populations and actually is very effective for things like autism, depression, etc. Another less practical mechanism is implantable BCIs, and these give you great fidelity, but we're not going to see these in the consumer realm anytime soon. Most appropriate for consumer is EEG, electroencephalography, where you're able to non-invasively, with dry sensors, track brain activity and create robust interactions real time. My own background in brain-computer interface comes out of the lab of Dr. Steve Mann. Dr. Mann is the accredited inventor of the wearable computer, and over a decade ago, he and I began collaborating in concerts where you could make music with your mind. 48 people at a time would sit in an audience, and by tracking changes in their brain state, very simple changes like changes in their alpha or beta brain state, we're able to translate those neural activities into sounds, so people could hear the sound of their own mind and create large-scale interactions. From there, we thought, this is amazing. We're literally controlling the world with our mind. What else can we do? So we wanted to create physical objects that you could move and show the power of your mind to interact with the world around you. This is the levitating chair. As you would relax, the BCI system would detect an increase in your alpha brainwave activity and cause the chair to rise to the ceiling, thanks to a handy-dandy winch that we had connected in the ceiling that would pull the chair to the top. From there, we went on to create games that you could play directly with your mind. And then we said, what's the biggest thing that we could possibly control with our brain? So at the Vancouver 2010 Winter Olympics, we allowed people in Vancouver to control some very, very large things. The lighting on the CN Tower, the Canadian Parliament buildings, and Niagara Falls. We allowed them to control these with their brain from across the country. Over the 17 days of the Olympics, 7,000 people got to individually interact with these massive icons using nothing but changes in their beta brain state activity. So from there, we got really kind of control happy. We started to thought control everything we could think of. We made thought controlled toasters. We made thought controlled slot car machines. And this is our ever popular thought controlled beer tap.
It'll pull down the handle when my voltmeter of my brainwaves hit over certain bands.
Did you get your sandwich ready? No.
I engage.
Oh, you eat it? Oh, no, we don't eat it. Oh, I can eat it now? You can eat it.
I relax.
I've been waiting for this.
And that's how you pour yourself a beer using your mind.
It's real. You want to come to our Christmas parties. Now, it turns out controlling stuff with your mind is fun, but it's really quite basic. At this point, we're really only at the point where you can have one or two dimmer switches that create these kinds of interactions. There's a theory in BCI that this is an active BCI, something that you're actively trying to control, and probably better adapted for brain-computer interface at this time is a passive BCI, something that naturally follows your own state. This concept was coined by Thorsten Zander and Christian Cote. Christian's actually the CTO of CUSP that you're about to hear from after me. In a passive BCI, the system listens to you and responds to you. This is something that we built around 2010, which was the responsive room, where all the elements of the room are tracking to your brain state so you don't have to do anything. As you would read, the light would get brighter. As you would relax, the music would begin to dim. As you would fall asleep, the lights would turn off and the blinds would close. So this was starting to be really interesting. This is not just about a human sort of directly controlling technology. This is about a human and technology being in relationship with one another, being able to learn from and respond to one another. We then realized that if you could be in relationship with your technology and it could learn about you, something even more important could happen. You could learn about you. And we started to create the space for introspective technologies, where technology's knowledge about you is then presented back to you so you could learn about yourself and engage with yourself more deeply. When we look at the kinds of technologies that are succeeding today, we are beyond sheer mechanical interactions. We're seeing technologies that enhance our human capabilities, technologies that lead towards greater connectivity, greater self-knowledge, greater relationship with other humans, as being the technologies that thrive and really support our daily interactions. So if you wanted to use an EEG device or brain-computer interface to understand something about yourself, in the past, this is how you do it. You'd get wired up with anywhere from 19 to 128 leads, and you'd be sitting very, very quietly in a hospital setting with a doctor on the other side of the room looking into your brain and trying to understand what was going on. Well, we wanted to change all that. So we made this device. This is Muse, the brain sensing headband. It is a slim, sleek, clinical-grade EEG. There are 4 sensors, 2 on the forehead and 2 behind the ears, and it slips on just like a pair of glasses. So you have EEG from FP1 and FP2 and T9 and T10, frontal and temporal, up to 500 hertz sampling rate, and it tracks your data and sends it to your smartphone or tablet with full spectrum EEG. Here's a comparison of Muse to a clinical grade system. This is compared to a ActiChamp, one of the gold standards in a clinical setting. And you can see the signal is virtually identical. Not only that, this device is available in Best Buy. So you truly now have clinical grade brain-computer interface systems available on consumer shelves. As we've all recognized, we're in a sensor revolution. We're at the point where we have sensors that track our sleeps, that track our steps, that give us real-time information about ourselves, and we've created this entire category called wearables that seems to be defining them. Well, there's something that was missing from this wearables category, and that was a wearable that actually was able to track your brain activity and give you information about yourself, which is fascinating because the brain really governs everything about our life. Our brain governs what we see, what we think, what we hear, everything about our experience. It also governs a lot of our disease state. 60 to 90% of all hospital visits are due to stress-related illness. Insufficient sleep costs $63 billion per year. 85% of us have low self-esteem. These are all problems, not just the body, but of the brain. So we wanted to find a mechanism that would allow us to solve some of these problems in our life that are governed by our brains. And the first way that we decided to do that was to take all of our knowledge and experience in brain-computer interface and build a meditation tool. Now, this may seem a little bit strange, but meditation and mindfulness is really probably one of the hottest topics today in healthcare. When you hear, meditation, you're thinking about big CEOs doing it, executives doing it, celebrities doing it, athletes doing it. It turns out that meditation's been validated in over 1,000 studies demonstrating its ability to improve your attention, decrease your stress, decrease your pain, decrease your chances of getting cancer, et cetera, et cetera. It's not some sort of weird practice. Meditation simply means training the brain to healthy and positive states. And meditation makes real change in the brain. This is the work of Dr. Sarah Lazar out of Harvard, demonstrating that meditation practice maintains the thickness of your prefrontal cortex as you age. Your prefrontal cortex is your attentional control center. Her work also demonstrated that 8 sessions of meditation is able to increase the density of your gray matter. In layman's terms, gray matter kind of equals smarter. It also decreases the activity of your amygdala, your fight or flight response, increases your insula, your bodily sensation, and on and on. So if meditation is so absolutely amazing for us, why don't more people do this spectacular introspective practice? Well, let's face it, it's really hard. There's this black box that's inside our head, and when you meditate, you sit there and you close your eyes and you kind of hope it all goes quiet, and it never really does, and you have no idea what's really going on, and it's really frustrating, and you give up. So we wanted to solve that problem. And we did that by creating an interaction where you can actually hear the sound of your own mind while you meditate. You can actually get real-time feedback on your brain activity. The metaphor we use is your mind is like the wind. We have a very sensitive algorithm that's able to determine when you're in a state of focused attention, when you're doing your meditation, and when your mind is wandering. And so when your mind is thinking, distracted, wandering, you hear it as windy, and as you come to your state of clear, focused attention, you quiet the winds. Gives you real-time feedback during the experience, and then afterwards, you're able to see your data and see what your own brain was doing moment by moment in your meditation. And then you're able to track your improvement and see the improvement both in your brain and in your life day after day. We have tens of thousands of consumers all over the world that use Muse daily to improve their lives in a wide variety of ways. And we constantly hear feedback about how people are now sleeping better, are less stressed, are more present with their kids, are more productive in their office, are now doing it as an entire team with their business and all seeing the improvements in their business, and on and on and on. This is a recent study that came out of Baycrest Hospital and University of Toronto using Muse, and they had average individuals muse for 10 minutes a day for 6 weeks. What they saw was a decrease in somatic symptoms, less headache, less pain, less nausea, an increase in calm, which is kind of obvious, and then very interestingly, an increase in cognitive performance. One of the tasks that it was sensitive to was the Stroop task. So in the Stroop task, you're supposed to read out the word. So if you read the word, it says blue. If you see the color, it also says blue, but you need to ignore the color. Now, if you've mused for 10 minutes a day for 6 weeks, you're going to say that says blue 20 milliseconds faster. And you're going to say that says blue 50 milliseconds faster. So it's improving your ability to make complex decisions in difficult situations with conflicting information. Kind of sounds like our lives. There are actually over 120 different research institutions who use Muse in a wide variety of different applications. One of the studies that's currently running is with the Mayo Clinic using Muse for breast cancer patients awaiting surgery to demonstrate a decrease in stress during the cancer care process, and likely also an increase in recovery times as well. Meditation's been demonstrated to have impact in all of these areas. The vast majority of our research institutions are working on some number of these to demonstrate improvements in people's daily lives. This is actually a paper that came out of another institution that was recently published in PLOS ONE, looking at our big data. So we actually have actually just under 1 million sessions of EEG currently logged. So we're able to do really fascinating things looking at population-wide data to give us new insights into the brain and to create new algorithms and experiences when you look at brain activity on broad scale. We also have a robust SDK so that any of the developers, from garage developers to our corporate partners, can create applications on the platform. We certainly will not have all the best ideas, and brain-computer interface is an arena where the entire world of development community is contributing to building the ideas, the applications, and the outcomes. So you get full spectrum EEG, accelerometer data, and then you're able to take either your full spectrum EEG and create your own algorithms, or use pre-processed and pre-canned algorithms that come in the SDK. Some of the fun things that have been done, we're seeing integration into other consumer electronics products. So I've seen quite a number of virtual reality integrations using EEG plus virtual reality. We're able to change state in a virtual environment. So your state of focus or your state of relaxation changes the gameplay. We've seen games for kids with ADHD and kids with autism or epilepsy, ADHD, autism, and anxiety, where they're able to do an interaction and then have a clinically validated tool that begins to demonstrate that they can improve their condition. This is a photo on the end from an exhibit that was at the Exploratorium, where you could move from installation to installation and control the lighting or control a thought-controlled drone and see your interactions come to life in real time. Now, where we look at where this technology is going, there are quite a number of different market opportunities where the platform of BCI can come to life. One of the market opportunities is in education. And we have a number of schools who are using Muse to improve kids' scores and to decrease their emotional reactivity in school. There was also an interesting paper that came out of MIT several years ago looking at engagement and learning. And they were able to demonstrate that kids learning in a digital environment where they were tracking their engagement levels were able to shift the digital environment when engagement flagged and have better learning outcomes overall. There's also huge opportunities for kids with ADHD. So kids with ADD have high levels of theta waves, dream state, and low levels of beta waves, focus state, in a typical ADHD scenario. And you're able to build games now where kids with ADD can upregulate their beta state simply by doing something like driving a car with their brain. So you're now able to make drug-free interventions for kids with ADHD. You look at the ADHD market alone, probably $12 billion a year is spent on ADHD medication. Entertainment is another great vertical. You saw the VR integrations, and right now they're quite basic. Right now you're really looking at modulation and focus or relaxation. The ultimate holy grail there is actually to be able to make a hands-free control in a VR environment. You'll probably end up with things like movies where people's brain state determines the outcome so that people can be more scared or more happy at the right point in the movie. You're going to see responsive musical experiences where music will tailor itself to your preferences and to your desires. And here we have actually the work of Tim in the bottom corner. If you remember David Rosenboom, the very, very first guy that I showed at the beginning of the history of BCI, there's he and Tim on stage at Mozart and the Mind, creating concerts with their own brain for the audience. Healthcare, tons of opportunity, from epilepsy systems that look like this or even smaller, where an individual with epilepsy can monitor their brain state throughout the day and then send a notification to their loved one if they have a seizure, or to their doctor. Healthcare interactions across the board once you have low-cost EEG. And then also in preventative wellness. There was a recent study that came out of Harvard demonstrating that 8 sessions of meditation is able to decrease healthcare costs by 43% the following year. So this kind of introspective technology doesn't just have impact in our brain, it has massive impact in our bodies and our healthcare systems. Automotive, always a great vertical. Right now you're looking at the state of the art around drowsiness detection and distracted driving. In the future, and this is still the far future, we will be able to potentially move cars and direct them with our brains. That's really not a try this at home project at the moment. And on the subject of home, the connected home is something that everybody gets excited about. Now, the connected home of the future we tend to think about as kind of mechanical process where it's going to turn on my coffee maker and turn on my lights because it knows I'm home. Well, there's a much bigger opportunity here for technology to really understand you, for technology to understand your emotional state, for technology to understand what you want, your own intentions and your desires. So it's not just going to be about, oh, my coffee maker knows I'm awake because an alarm went off, so it's going to turn on. Right now, with our technology, your coffee maker can know that you're awake because we can readily see the change between sleep states and wake states. Your coffee maker and your home could also know the mood that you woke up with, and then modulate lighting systems and create a supportive environment to help you transform your mood throughout the day so that you can feel and be your best. So I've painted a future of the possibilities, but I haven't explained how we're going to get there. So I'm now going to hand over the microphone to Tim, who's going to take you through some of the detailed signal processing backend, some of the software requirements, and talk about how we get to the space of pervasive computing to make these kinds of examples a reality.
Okay, can you hear me? Doing all right? Okay, great. Fantastic. Thanks, Ariel. So that was a great introduction to the current and future possibilities and opportunities for brain-computer interfaces. And Ariel there ended with a really interesting and cool example of the connected home, wherein the environment around you is responding to your state. And imagine that if you were to extend that further and you have a scenario where you're moving from your office to your car to your home, and throughout that entire process your state is being tracked and the environment around you is modifying itself to better support your neural or your cognitive state. That requires pervasive computing, which extends from the concepts of ubiquitous computing that were first coined by Mark Weiser at Xerox PARC. And so Mark had this wonderful quote where he says, "The most profound technologies are those that disappear. They weave themselves into the fabric of everyday life until they're indistinguishable from it." And that's really at the core of a lot of what we're seeing in terms of our mobile technology now, wearables. They're becoming invisible so that we don't even notice they're there. And the environment, they interact with the environment transparently in this pervasive way. You can wear them 24/7 all day, switch between different environments, and it's just like a part of your skin, essentially, or a part of your clothing. So Cust's mission, my company, is really to enable the integration of advanced neurotechnology into everyday life, anytime and anywhere. And there's a number of challenges and opportunities along that path, which I'm going to highlight throughout the remainder of the talk. First of all, the unobtrusivity of brain sensing technology. There's a huge challenge and opportunity. Ariel's hardware is a great step in that direction. It basically enables us to have lightweight, comfortable, and aesthetic hardware that can sense your brain state. Another key challenge is that of computational tools being powerful enough to be able to decode brain states. This is a hard problem. So understanding the relationship between brain activity and our behavior and our cognitive states is not a solved challenge by any means. A third challenge is having standardized, pervasive neurotechnology middleware. And I'll talk a lot about this throughout this discussion, how we can have ecosystems that allow third-party applications to build on top of neurotechnology and basically have sort of one-to-many type system architectures. So Cusp Technology, our solution to this problem is plug-and-play APIs for neurotechnology. So we provide the world's first platform for advanced neurocomputation that operates on the cloud, and it brings real-time brain-body signal processing and state decoding to any device, any application, anytime and anywhere. And there's two products that are currently under closed beta that will be fully on the market within the next quarter or so. And the first is NeuroScale, which is a scalable real-time API platform for processing EEG and other biosignals. And this is a sensor-agnostic platform. So it allows you to record EEG, EKG, EMG, all kinds of other input devices can work on NeuroScale. So you can integrate multiple different sensors and do signal processing on them and make sense and interpret those signals. It also uses a RESTful API, which basically just means that if your application can connect to the internet, then it can be made bio or brain aware. And so that's a huge step towards pervasivity and ubiquity for neurotechnology. NeuroPipe is an extensible Python-based computational platform for biosignal processing. It's an engine. It's the workhorse of our state decoding algorithms. And we actually designed this to support a very wide ecosystem of algorithms. There's over 100 algorithms on there right now that are from state-of-the-art machine learning signal processing tailored towards neural state decoding and biostate decoding. But it's also extremely easy to use. It has a graphical user interface that allows you to drag and drop widgets and wire them up and build your own pipelines if you're a developer or a researcher. And if you're not, these pipelines deploy on NeuroScale that allows you to then access them anywhere through this REST API. 5 lines of code, 6 lines of code, and you can extract a meaningful and complex brain state without needing to know really very much about how the actual neural system works. So I'll just show you a couple examples here of NeuroScale and how that's enabling pervasive brain-computer interface applications. Here we have an example with the Muse. This is a game called Tractor Beam. It's a cognitive training game. And so what happens is the EEG data streams up to our servers through an app on your phone. You put on, say, a Muse headset. You're extracting the brain activity through that, and we do some adaptive feature extraction, and we calculate measures related to how much you're focusing or attending to different things, similar to what Ariel was talking about earlier in terms of what we've discovered recently about different brain rhythms and their relationship to attention, for instance, in ADHD or in autistic populations. So you can extract these metrics and feed those back into the phone. In the game, you have these little orb that is being tugged around like a sort of tug-of-war with this tractor beam, like one of those cool Star Trek tractor beams. And the cool thing about this is that it's a multiplayer, so it can be a massive multiplayer game because it works on the internet. All the state decoding's on the internet. Nothing happens locally except just visualizing your state and sending data to the cloud. So you can have hundreds of people who are competing with each other, whose brains are competing with each other to play this game. Here's an example of what I mean by pervasive BCI, that it should work anytime and anywhere. And so this is NeuroScale operating. We're playing Tractor Beam, this game, on planes, for instance. So here we are about 30,000 feet in the air on Virgin America. And the gaming systems here are, there's no local communication, so all the synchronization between these two is going through satellite Wi-Fi. And so as we're focusing our attention, we're pulling the little orb towards us, and now he's competing with me, and I pull it towards me, and we play this neural game together. It also works on trains. So then we hop off the plane. This was a real scenario, and this was all contiguous. We jumped off the plane, we went through security, we got on BART in San Francisco, And now we continue to play the game. And we have other guys in San Diego who are the other players here, so we're actually able to play a distributed Neurogame in real time over these, in this case, over 3G. And another cool thing about this is that it works in automobiles. I don't know if any of you guys saw the planes, trains, and automobiles. I was very excited when we finally did this because I could unify the three and say it's planes, trains, and automobiles that it works on. This is an example of, Ariel gave a cool introduction to the possibilities for applications, brain-computer interfaces that work in vehicles. For instance, the car being aware of your mental state, your alertness, how much you're focusing, or you can imagine a car that adapts its automated intelligence system based on how well the driver is going to be able to respond to an unexpected event like somebody jumping in front of them on the road. We actually are conducting research with a large consortium and Army research labs on exactly this topic, how we can look at neural states in the vehicle. But this is an example. This is the world's first demonstration, to my knowledge, of a closed-loop, cloud-based brain-computer interface in a vehicle. And so what we're doing here is we're wearing this is my chief data officer, Nima Bigdeli Shamlo, wearing a high-density dry wearable EEG system. And he's hearing tones being played in the car. Standard tones, beep, 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 and occasionally there's a slight pitch deviated tone called an oddball, and that's a little beep, and that happens with 15% probability. And what we're doing is we're streaming the data to the cloud, and we're applying a very sophisticated signal processing and machine learning pipeline in NeuroPipe. This would not be able to be computed on a cell phone under current technology without you exhausting your battery within a very short period of time. And what that does is it predicts whether the tone you heard was the standard or the oddball, and that's modulated by your attention as well. So how much you're paying attention to your environment or just kind of disconnecting and detaching. Then it sends that probability back, and you can have that fed right back into the vehicle. In this case, we're just displaying it such that when this bar moves to the left, it's the probability of the tone that you just heard being an oddball, the little pitch deviated tone. When it moves to the right, it's the probability of it being a standard. So we're detecting the brain's ability to discriminate between these two different stimuli. Now I'm going to show you an example, and this is all happening in real time. So I'll just show you an example here. Playing around with iMovie around this time, getting very excited. Here, carried away. So this is Mike Chi from Cognionics supported this hardware for this. So let me just skip here. So we're a little late on time, so I'll just skip here to a little point. So we train the model first. That takes a few seconds. In this case, maybe about a few minutes, about 15 minutes to calibrate the model. You have to collect some training examples, and I'll talk about how you can get around that a little bit later. And then as soon as we've done that, now in real time, we're playing back the tones and we're classifying the responses. So here you can see it. So you hear the beeps, and you're seeing the few milliseconds later, few hundred milliseconds later, you see the response of the classifier. Green means that it's correct. Whenever it goes red, it means that the classifier is incorrect. So it's very, very accurate in this case. So there's the oddball, boop, and you can see that we can predict it. We can detect that little pitch deviated tone. And there's the, that's just the EEG headset in this case. So this is a noisy environment. He was looking very good, actually. Very handsome. And so here, so you can see that there's a very low latency response. And even these little beeps that happen oh so infrequently, we can pick up the neural signature of that within milliseconds and make a prediction of it in that vehicle. So that's very exciting because it means that we're taking something that this sort of example was, even in the lab, these algorithms were have only really been used in the last couple years. So the algorithm for this was published maybe 3 years ago and has only really been extensively used within the last year and a half. And we're able to take that and make that accessible in these real-world environments through this platform. So now I want to dial back a little bit and talk a little bit more about the motivation for our trajectory and some of the more detailed aspects of the challenges that we face in creating pervasive brain-computer interfaces. So just back to our past, our origin is in academia. The founding team, we are all researchers at the Institute for Neurocomputation at UCSD. and particularly the Schwartz Center for Computational Neuroscience. And there we developed a lot of software that became very widely used for neuroscience analysis. We worked on the EEG lab environment. I didn't invent the EEG lab, that was Arnaud Delorme, but we developed a large number of tools for that ecosystem, and we're heavily involved in that process. We also created very visible demonstrations like the glass brain, which was the world's first virtual reality fly-through of an active brain, where we're decoding neural states in real time and able to fly through your own brain in VR. I'll show a quick example of that later. And then a wide array of different software tools for decoding brain states. And our goal was really to try to see how we could take what we'd learned from the lab and find ways to translate that into the real world. Now, one of the things that we did a little while back is the IEEE had their 100-year anniversary, the proceedings of the IEEE in 2012. And they had a special centennial issue where they approached a few labs around the world, like 100 labs around the world in a wide range of topics, from nanotechnology to space technology to neuroscience, neural interfaces, and asked them to write about the last 100 years and the next 100 years of their field. So we and some of our colleagues wrote a trio of articles for this on the current and future of brain-computer interfaces. And I would encourage any of you to read this trio because it kind of summarizes the hardware, where the hardware solutions are currently and where they're going for decoding brain states, as well as signal processing, where that is and where it's going, and then what are the applications for coming decades. In our article, we drew up this diagram. So this was my attempt to try to, one, get a naked man into an IEEE journal. Two was to try to sort of create an example of a future framework that incorporates many of the key components that I see and we see in the BCI field as being instrumental for making BCIs pervasive. And so I'll just quickly go through some of these. Some of the opportunities here. So the first is having non-invasive multimodal and wearable sensors for measuring brain and body activity in the real world. I talked about that a little bit earlier when I talked about Mark Weiser, but we need to be able to extract multiple sources of activity from the brain and body and do things useful with them, and that needs to be wearable, high SNR, low cost, and so on and so forth. The other another very key component of this is improved real-time signal processing for and machine learning for artifact mitigation, getting rid of noise, meaningful feature extraction, which is not a trivial problem, and neurocognitive state identification in real-world environments. And I'll mention a little bit more about that. And you saw some examples of that with the in-vehicle neural state decoding. Two interesting directions in that space are neural system identification, being able to get at the networks and nodes of the brain in real time and make sense of what they're doing, and multimodal data fusion, mashing up not just brain, but brain with what your eyes are looking at, what your heart rate, what your heart's doing, what your muscles are doing, and context. Another interesting and somewhat overlooked area in brain-computer interfaces has been population inference. So that's basically aggregating data from many, many people. Ariel showed a very cool example of what they're doing with Muse, with 1 million sessions and being able to do big data analytics on that. We also look at this in our own projects. And this ultimately will allow us, by aggregating data from many people, to apply sophisticated transfer learning and collaborative filtering type algorithms to produce universal classifiers, which basically are, imagine that you just put on a headset or you put on a device, and immediately the device is able to interpret your brain state, and you can interact with the world through that. That's typically not the way a brain-computer interface works. There's a calibration period normally where you have to perform various tasks and sort of give the machine labeled examples of what your brain activity looks like in different states. We want to get around all of that by using information from other people that are more similar to you, and using their tagged neural information to make predictions about your own state. Finally, another exciting area is using that information from multiple people as well as large bodies of empirical data from science as principled model constraints or priors on machine learning algorithms that can decode your brain state. And the last thing is a very cool opportunity. Again, this is what we focus our attention on, is standardized neurotechnology software platforms that can support diverse and pervasive consumer and medical applications. So the traditional BCI was a sort of a a sort of linear path where you would you would engineer a hardware solution, software solution, and an application or an interface for a specific application or user population. We believe that the future of BCIs is one-to-many or many-to-many, where you have a device that has where many different neural states can be decoded from that, and then even more applications can build on top of that, without any one layer needing to necessarily know much about how any other layer works or functions. Okay, so quickly, just a range of different wearable EEG solutions. I'm going to go through a couple of those different categories real quick here and give you a bit of the technical overview. So there's a range of different wearable EEG solutions out there. The Muse is really a great example of a lightweight wearable and aesthetic sensor package that sits at about 4 active channels. You can go to less wearable, more bulky, but higher density systems like Cognionics over here, and there's a range in between of a spectrum of different devices. One of the interesting things that we're very interested in is, as I mentioned, multimodal data acquisition, and also being able to have systems that can extract information from multiple different EEG devices. So one of the technologies that we developed when we were at the Swartz Center was the lab streaming layer. It's a free and open source platform. Christian Kothe primarily led development of this, although a few other individuals were involved. And it basically allows you to extract data from over 23 different device classes that range from human input devices to EEG systems, to eye trackers, and it supports the majority of the EEG systems that are out there right now, and a number of consumer EEG companies support this technology. So that lets you get the data off the device and then into your hands for signal processing. Ariel showed a quick picture of this earlier. This was a study that we recently published in an IEEE journal, which was the first demonstration of a dry, high-density wearable BCI system where we could do neural state decoding in real time. We could localize sources in real time and make cognitive predictions about somebody's state, in this case detecting whether they made a mistake or not. All this in real time using a totally wearable wireless mobile sensor. So really the future of wearable BCIs is here. And we're able to do things that were only possible to do in the lab. Now we can take it out into the real world. And that really broadens the applications. Here's an example of taking this sort of stuff out into the real world. So this is what I would call the wild. This is an example with at NVIDIA GTC keynote, the GPU Technology Conference. We did a demonstration there with Adam Gazzaley and Mickey Hart from the Grateful Dead, the drummer from the Grateful Dead. This was a system called Neuro Drummer and the Glass Brain. And Neuro Drummer is a virtual reality cognitive gaming environment, which is putting pressure on you to basically be able to switch flexibly between different tasks. The Glass Brain is this what I mentioned earlier, a virtual reality fly-through of an active brain, but underneath it is very advanced signal processing for decoding your neural states in real time. Basically, the paper that I just showed you earlier is at the basis of this. Here I'll show you an example that's playing. So Mickey's playing he's playing his drums. He's playing with his game. Asteroids come up. He has to switch tasks and break them. While it's happening, I'm here on the right, flying through his brain in virtual reality, seeing the neural circuits and how they're changing over time. And the goal of these systems is to close the loop, where the neural states feed back into the game environment and adapt the game to put selective pressure on particular neural circuits that are known to decline with age, for instance, or that are deficient in certain populations. And that's really at the heart of what we're looking at, how we modify and change specific localized neural circuits and specific brain networks in real time. So that was pretty exciting doing that. We also, this Mozart in the Mind it's a festival that I direct in San Diego, and we've had the opportunity to play around with a lot of cool technology using Muse in a lot of these installations, and also did the Glass Brain there, which was a really kind of crazy and into the wild type of scenario, because as you can see here, and I'll just skip here, we did a full-on crazy-ass rain dance, Mickey Hart style, Grateful Dead, drumming circle with neurotechnology all integrated into the same environment, which was probably something that had never really been done before. So we had like 700 people drumming, and Mickey was dancing, and we were tracking his brain state, doing all of that in real time. If you're interested in any of these kinds of installations, I have a book chapter on this in this book, More Playful Interfaces, about a whole range of different neurotechnology applications two playful interfaces and social interfaces that mediate between the brain and music and art. Okay, so in those applications, we saw that there was a lot of active movement. There was a lot of noise being generated by these sensors. This is a very common scenario. When you're moving, you generate huge amounts of electrical artifacts that contaminate the EEG. And we have algorithms that can remove those in real time. So this is an example of ambulation with a wearable dry EEG sensor. On the left is the contaminated data with the artifacts, and on the right is the clean data. When you're just walking lightly, it's not so bad. But you'll notice a significant change as soon as I start jogging and moving actively. Then we start to see very substantial high variance artifacts on the left, but notice that we can completely remove those and track the underlying subspace of brain activity in real time that's not related to the artifacts. Just very briefly, I want to point out something. I mentioned earlier that one of the big challenges is we need computational methods that can decode complex brain states. The brain is a complex organ, and its relationship to behavior is complex. I just want to give you a picture of how that works generally. In the brain, you have unobserved functional source coupling and dynamics. Those are modulated by external inputs, sensation, that generates the EEG activity that you observe. That's contaminated heavily by these artifacts I mentioned. Heart, muscle, electromagnetic activity from power lines and other sorts of things. The neural circuits generate behavioral outputs or action. And that changes things in the world, which ultimately influences, again, your sensation. And we can actually close that loop or modify that loop to change the neural circuits in the brain in a real-time context. Now, future BCI technologies will benefit from, one, separating signal from noise. It's absolutely essential. One of the most critical issues with EEG is solving that problem. And mapping brain dynamics at the spatial scale of functional regions and the temporal scale of neurocognitive events. So for instance, the speed of thought. This means at the millisecond scale or tens of millisecond scale. And leveraging machine learning to solve a bit of that problem. Quick example of how we can take that concept of tracking those neurodynamics and then make it pervasive. I showed you the glass brain there. Very cool, very advanced technology. Well, we can do that on a cell phone now. Never been done before. Here's an example of a pipeline that does that. This is coming from a 21-channel EEG system that's wearable but wet. Here I am in San Francisco, and I'm seeing my CTO's brain live on my cell phone. He's hundreds of miles away in San Diego, wearing the EEG system, and I'm able to track and view his brain in real time, not just the activity on the surface of the brain, but the functional regions and their activation, and even the connections between those areas, the neural circuits, the same technology that powers the glass brain on your cell phone. And so this is all powered by the telecommunications infrastructures that are now rich and mature in our world, and it's becoming very exciting. So when we have pervasive BCI systems where we can acquire data anytime, anywhere, we'll also be able to acquire data from a lot of people. Again, Ariel mentioned what Muse is doing in that context. Imagine when we can extract information from hundreds or thousands or millions of people, what sorts of new questions we can answer. This is an example of a study done by some of our group where what they did is mashed up brain imaging and big data analytics to analyze over 500,000 sources over hundreds of people and find out the hotspots in the brain that are most common across different people. And so here you can see the constellation of different sources, and these are the key hotspots that are common across, in terms of the brain regions across different people. And you see critical decision-making areas and motor areas that show very similar activity. This is sort of showing you what areas show similar activity across different people. We're building BCI data repositories at CUSP in collaboration with UTSA and the CAN-CTA consortium, where we're aggregating millions of EEG sessions and tagging them and being able to mine them and relate different neural events to different types of behavior. We have something called the PrEP pipeline you might be interested in, which is a standardized pre-processing pipeline for big data analysis. And then again, cool things like, I think this is probably the biggest data repository that I've heard of. Which over 1 million Muse EEG sessions. And this opens up a whole lot of new opportunities for transfer learning, for instance, where you can take data from one population and build models for a new individual without having to calibrate on the specific individual. Narissa just mentioned briefly here that there are a range of industry standards for consumer EEG that we're working on, and by the CTA, so I encourage you to check this out, the R64WG3, for instance. I'm going to skip over some of the future directions because Ariel already mentioned that and we're short on time. But I will say very briefly that one thing that's very interesting to me in terms of future directions are new wearable and lightweight adhesive sensors and new types of implant technologies that allow you to extract information at a lower spatial scale in the brain with minimally invasive surgeries. And that's going to lead to a whole new range of very cool applications. So I'll leave you with this one point that Ariel pointed out, the smart car or home of the future. You can imagine a scenario here where the neural state's being decoded, broadcast to your environment, but sophisticated metrics are being calculated on the cloud, for instance in neuroscale, and that's being used to adapt the environment around you to support your well-being, to support a rehabilitation for maybe disease states. So you're somebody who has Parkinson's, your home can be supportive towards that. Or, for instance, just enhancing your general quality of life by creating a smart home that is really reflecting your mood state, your emotional state, and that's the sort of stuff that we're working towards and InteraXon as well. So I'll leave that here so you can see what some of the contact information looks like for us. And I think there's a discount code for Muse out there too. Thank you.
Well, I'm told by our chair that we have about 10 minutes for questions. I just want to remind everybody who may come in late that the program, that's published program, add 30 minutes to it, will be starting 30 minutes later in order to fit in the extra keynotes. Any questions or comments? Or
yeah, Stu, let me just make one remark. Okay, we had a hard time to shut down the questions on Saturday evening. And both of them, I really appreciate their making their availability to come to this. And I'm sure you're excited with that. Everybody's brain probably grow by an inch by now. But we would like to accommodate. Did you say 2 questions?
Yeah, well, he said 10 minutes, right?
10 minutes? Okay. So, okay, Richard, you get the first one.
Thank you. I'd appreciate if either of you can share some experience with I imagine the most easy environments are noise-free at home, but what are the hostile environments that may prevent this from having clear readings or take longer for each signal group you're looking for? Does this preclude it from some industrial environments and work or schools near power lines, for example?
Sure. So we have a 50 or 60 hertz notch filter, depending on if you're in Europe or in North America. So noise from power lines, for example, thank you. Noise from power lines, for example, can actually readily be filtered out. When you're looking at a hospital environment, it doesn't really matter if you're in a big concrete closed box because you can do local engagement just between your mobile device and the headset. You don't have to go up to the cloud, so you can exist within a local environment, or you can have an environment where there's still sufficient Wi-Fi in a hotspot environment to be able to run a neuroscale type environment that uses the cloud. So for the most part, I mean, the worst experience I've ever had was in a closed shipping container with early technology about 10 years ago, where there was just so much electrical noise bouncing around that we couldn't do it. At this point, we've actually moved beyond that and been able to ground pretty sufficiently to have a relatively robust interaction even on an airplane.
Yeah, I would also add to that just to say that, so that prep pipeline that I mentioned, a lot of what we worked on back in the day was denoising algorithms exactly for this issue, like getting rid of line noise. And so you can use adaptive regression techniques, you can use multi-taper decompositions, various kinds of signal processing methods to also deal with that, in addition to having excellent grounding, active sensors, and things like that that on the hardware level mitigate it. That prep pipeline I mentioned has built into it automated noise reduction for line noise. So it's actually a reasonably solvable problem, line noise specifically. Other sources of noise can be much more difficult to deal with. Yeah.
Yeah, thank you, Ariel and Tim, for that very engaging presentation. My question is the Muse headset capable of doing any type of source localization? And if the answer is no or not really, then what would be the motivation for a consumer wearable device that could do very precise source localization?
I'm going to actually let you answer that because you've done some basic source localization.
Yeah, so the key thing with source localization is large number of channels distributed over the brain. That being said, the Muse does have multiple sensors that tracks activity from different parts of the brain. Well, we have done spatial filtering with the Muse, which allows us to get rid of artifacts, for instance, and separate that from brain activity. So we can do that. In terms of being able, with 4 channels, to be able to localize precisely sources in the brain, I think that's a difficult challenge. I don't want to say it's impossible because the signal processing challenges are not yet fully unraveled. For instance, compressive sensing totally changed what we thought about the Nyquist limit. So people are looking at things like compressive sensing for very low channel density systems. But generally, our rule of thumb is, the more channels, the better the spatial resolution. And above about 16 to 19 channels is where you start to get towards what you might be able to use in a clinical scenario in terms of source localization. Those are my comments on it.
Yeah, so at this point, with 4 channels, you can generally get kind of quadrant-style localization. You can't get precise localization. And the amount of localization that's required really depends on the application. So for most BCI-type engagements, localization is not required at this point. When you're starting to look on the circuit level, that's when you want to get to a localization.
You showed us many exciting applications and solutions about using EEG or brain-computer interface. I think these are very exciting. But according to my understanding, all of these are currently just read-only. I mean, reading signal from brain. So do you expect there will be some read and write non-invasive solution applications in the next few years? Like not only reading signal from your brain, but using some non-invasive way to feed signals back to your brain.
So we've certainly seen laboratory examples of read-write. There was the incredible example that came out of the University of Washington where an individual in one laboratory was clicking a mouse and an individual caused an individual in another laboratory to also click the mouse. You were really seeing one person's brain map onto another brain. So it was actually a very simple example with profound impact. Read-write is really only at the level of laboratory-style engagements. You're starting to see dense multi-channel EEG sitting alongside electrical stimulation devices so that you can do closed-loop reading and writing. The applications here tend to be very exclusively in the medical domain and probably should remain in that domain for a good long time until they are sufficiently robust and validated to make it out to the consumer space. So we're talking probably 15 years. That said, you are seeing basic write, not read-write, just basic write applications in the consumer market with devices like Think that electrically stimulate not your brain but your vagal nerve to change brain state. And the jury's out on transcranial direct stimulation as to its efficacy, but we are starting to see it flow into the population.
I'll just add to that just to say that so interestingly, the project with which was Rao's group at UW, where we're doing the TMS-based thing, 10 years before, Kevin Warwick demonstrated the same kind of technology, but with a EMG-based type sensor. So the technology's been there for writing somewhat to the neural system with stimulation. But I wanted to comment on one thing, which is this is a huge area of focus in the neurosciences right now. Particularly, DARPA has a project called the cortical modem. And the goal is exactly what you mentioned, I/O. But this is using technologies that are way beyond what we consider even now invasive, optogenetics. So modifying the actual genetic structure of your neurons to respond to light and to fire in response to light. This is not going to be in a consumer application anytime in the near future, suffice it to say. But that allows you to target specific neural circuits with wavelength-coded light and allowing you to actually activate those circuits and produce, for instance, visual images directly through stimulating the visual cortex rather than through a retinal implant. It's very exciting. If you just Google direct neural interface, you'll see some interesting stuff on that. It's a whole new field of neurotechnology.
The work of Ed Boyden at MIT is primarily also on optogenetics.
Right.
Tip, I have a question I want to ask you. Actually, I'm a signal processing person, okay? My focus is mainly on time frequency analysis, optimization, machine learning, particularly for deep learning and convolutional neural networks, something like that, okay? Actually, I have one project with University of Surrey working exactly on BCI. So your presentation is very exciting for me. But one thing which is the challenge which is we are facing on that project is that we find that it's very difficult to have universal classifier to understand the brain signal. Particularly, okay, what we have been done is only we can understand some very simple signal, for example, left and right, forward, backward, something like that. But you know, human is very complicated, particularly for motion. For example, we want to understand how the brain to control how the hand movement. Okay, not only left, right, something like that. You know, more than actually it's more than this one, right? But how can we understand, you know, using this ECG signal, which is currently we are working on that, but we have lots of problems. We don't know what to proceed actually. Do you have any idea or suggestion that how can we proceed?
Yeah, I'll just briefly point you to, instead, I could give you a long-winded answer, but in the interest of time, I won't. If you look at, I would recommend looking at some papers by Donguri Wu, who's a researcher who's formerly at GE, and has been doing a lot of really good work on transfer learning and active class selection, and now looking at deep learning and ways in which that can be used to transfer data and build universal classifiers. Two things. One is, you know, having cool, sophisticated methods that are able to do this in a principled way, and for that I encourage you to look at that. Also look at Maurice Grosse-Ventrup's work from Tübingen, and that's also on the same topic. But the other thing is just having a lot of data. You need a lot of different examples because there's huge variability in different individuals. And that's the whole reason why you need calibration data from one specific individual, is basically learn what's the variability for that individual. So having more examples, more big data repositories out there, I think is going to completely change the challenge of that particular problem. Yeah. So I know you probably want a more sophisticated answer. We could talk more about it after, but I would have to then launch into a 10-minute digression.
Anything to add?
That was good. Also, having longitudinal data from a single individual helps you ultimately build universal classifiers. So one of the things that we do is we have a large data pool that we read against, and then we also have individual data pools. You're constantly modifying your own classifier, and we're building new classifiers for you and building on it every time you use the experience. And so ultimately, we're able to get rid of any calibration period because we actually understand your own neural dynamics.
Okay. Due to time limitation, and again, I'd like to thank Stu to conduct the question and answers for this. But before we close this, I'd like to just emphasize one thing. You look at these two outstanding speakers. They are scientists, they are also artists, and they are also people like you and me, and their accomplishment up to this point is just incredible. Yes, we all recognize the challenges we're facing, but don't underestimate them, don't underestimate you. Solutions can come about. Don't be stuck with the algorithms only. Okay, with this, I would like to invite everybody to join in a big round of applause for both Ariel Garten and Tim Mullen. Thank you very much. Thank you. This concludes the first session of the keynotes. We would like to invite you to receive the plaque, and I would like to introduce the General Chair to provide our token gratitude to both of them.
Thank you very much for being here, for the nice session you spent with our young professionals, and of course for this nice keynote speech, and a brief present for you.